Good evening, everyone. Welcome to the 13th episode of Nodutalk. During these 3 months, what we have done, we have uploaded all the past episodes of Nodutalk on the YouTube. And in this episode, we are going to cover problems related to dimensions of the casting, to cover the customer's requirement for castings, dimension of the machine castings, quality of the section of the castings, type of non-conformities, and non-conformities related to incorrect dimension, deformation, and shape difference. So now I hand over to Mr. Staff Hendrieckx.
Good evening, everyone. So the customer is the one who set the requirements for every casting, and the international standards concern material. We have the dimensions of the machine casting. We have the quality of the section of the casting, and we have extra requirements concerning the features as our surface roughness. These are the four requirements of type of requirements that the customer can put when he orders casting. So the dimensions, that's the topic for today. Dimensions are given on the machining drawing, and some customers have a casting drawing, and there are standards about the casting dimension. Please pay attention, because a machining drawing is very, very difficult for every foundry and should not be accepted just like that. Why? We don't know what the machining stock is that the customer wants to have. So please, if possible, discuss with him until there is a casting drawing. And for the casting drawing, we have standards who can guide us for having the tolerances, but not on the machining drawing, because a machining drawing is for the machining shop and is not for the foundry. Please always try to get a casting drawing. If we have the section, the soundness of the section and the surface, porosity, inclusions, cracks, or items that every foundry will meet, not every day, but regularly. And the requirements for all of this for different parts of the casting can be different depending on the part of the casting, so that the casting does not have a requirement on the whole, but can also have requirements for details of the casting. So we have also seen that the roughness about machine castings is, let's say, internationally applied and accepted, but the machine castings is not for the foundry. That's for the customer who has to do it. But the roughness about the non-machine casting parts, surfaces, is less applied and different, mainly on the type of molding we have. And we will see that during the whole series. We have material-related non-conformities, dimensional non-conformities, quality-related, that's of the section, and the surface roughness-related. But now we will do it about dimensions. The dimensions means also the shape of the casting, because if the shape of the casting is not perfect, there is a deformation or whatever, then the dimensions are also not okay anymore. And the problems we can have is an incorrect dimension, a deformation, shape difference, surface sunk, which is in real kind of shrinkage, but ends up as a surface sunk in ductile iron, and can also be missing details. Please, the international standard who is applied all over Europe, and I think also in the rest of the world, is the EN ISO 8062, but there is a new one, ISO. That means it's not really explicitly applied, but please follow him, 8062 in 2015. The customer can choose the class in general or different at different locations. What I said, the dimensions can say, okay, it's for the whole casting, but it can also say some details of the castings will have that class of tolerance. Remember one thing, that the wall thickness always lead one class less than the dimensions of the casting. Why? The wall thickness is very thin, and therefore it's taken one class less than the rest. You can see here the terms who are used there, and I see the dimensional casting tolerances and the tolerance grade. You see the geometrical casting tolerances, that's more the shape, also tolerance and the grade. You have the required machining allowances, and that's also with the grade. You have the tapering, plus or minus, that's because the casting or the pattern must be able to remove from the mold, so you have tapering, and we have the surface mismatch. Machining is here, and the customer should say which machining allowance he is asking for, and that depends on how we will machine, with type of machining will done, turning, milling, or whatever. It's him who does look at it. I should only say one thing. Please remember, especially when we have bigger castings, that the top of a casting should always have more machining allowance than the bottom, while all the let's say the inclusions and everything float up in the casting, especially thicker castings, and therefore we need some more machining allowance. This is the main table where we should see, and depending on the class from 1 to 16, it's a lot, and the dimensions are divided in a group minus 25 millimeters, then from 25 to 100, then from 100 to 400, and if you go more than 400, then let's say you become in the series of big, large castings who will have really tons, not 1 ton, but maybe 5 ton, 10 ton, and so further. These are really the basic of every choice you make for the casting tolerances. It's linear. If you take, for instance, the class 7 for the dimensions, then the wall thickness should have class 8, as I told before. Always do that. Wall thickness must have 1 class higher than the class for the dimensions itself. It's also mentioned below the text there in remark A. Please, every standard, international standard, has annexes. And in the annexes, they are given mostly informative information, data. This again is informative. That means it's not required, but don't think these, let's say, the value of these is not important. It's very important because they have checked a lot of foundries, and becoming due to that result, they have said, okay, this is what's happening in the world, and you should use this. If you see the B1 table gives for long series and mass production. And if you see there, then you can see that gray iron and ductile iron have the same classes, but for sand hand molding in series, it's 11 to 14, when it's machine molding and shell molding, you can see it's 8 to 12. So that means that the sand cast hand molding is less accurate than the machine mold and shell molding casting. You see also investment castings, they have a much more strict tolerance. But the B2 is for short series and single production. Single production, that's of course okay, everyone knows what it is. Short series, what is it? Well, mostly what we say here, short series, is a matter of, let's say, per order 5 casting. And the order is coming back later, but with quite some time in between. Then we call it a short series. And there you see that for clay bounded, gray sand, as a matter of fact, it's 13 to 15, where we see that for the serial production, it's 11 to 14. So it's less accurate if you have clay bounded. Chemical bounded sand is 11 to 14, and that's the same like the hand molding from the mass production. Please don't go more accurate than this. If I am involved in problems between a foundry and a customer, then it's in 20-25% of the cases about the tolerance. And what happened, that the customer asked a tolerance, and the foundry has said nothing or has agreed with it. And then later on, they found out that it's difficult to achieve if to say nearly nothing, because you should achieve it 100% of the time. And these figures you can achieve, but much better than this, forget about it. You will get problems if the customer likes to do it. Never forget this. Discuss it with the customer. It's informative, but you can agree with the customer and convince him that it are real figures. Okay, when you have incorrect dimensions, what is the root cause? That's mainly the shrinkage during the solidification. And how is that? That's because the pattern dimensions are incorrect for giving a correct casting dimension. The real shrinkage cannot be taken from the literature. I know people and they have, let's say, a paper on the wall, and there is for every material, there is a shrinkage, a pattern shrinkage. Don't think it's okay. We will see it in the next slide. This is the shrinkage you can imagine. If you see in number 2, a ductile iron as cast average 1.2, but it can vary from 0.9 to 1.4. So heat-treated ductile iron, especially when it's made ferritic, is 0.5% average, and it's 0.3 to 0.7. So please think of that if you heat treat the casting, especially ferritize it, the dimensions will be bigger than a casting with not heat treat. And I have also mentioned some other literature, and they say instead of 1.2, they say 0.85, 0.8 to 0.9, and heat treated 0.5, 0.3 to 0.7. Please remember from this that there is no fixed shrinkage percentage. You will have to find out yourself, and you will have to use your experience to find the correct. So if the dimensions are too large, it's about an incorrect instruction can be around an incorrect instruction during the volume shrinkage. We will see on that. Remember that ductile iron casting has a lot of shrinkage during solidification, but after a while it expands again. And this expansion can be so, let's say, large that depending on the mold, it can even open the mold so that the volume becomes bigger than before. That's one thing we will see in the next slide how it works. And the second thing is the split line. We see so many castings with a flash at the split line. Don't forget about this. If there is a flash at the split line, your dimensions concerning the split line are bigger, and you will have a bigger casting instead of the one you are, let's say, expecting. The split line is mostly due to insufficient clamping or weight of mold that you plan. And the third one is the heat treatment that's not planned. I have seen many times then they must have a ferritic ductile iron casting. It's not ferritic. They don't have the elongation during the tensile test, and for making it ferritic they do a heat treatment. When they do a heat treatment, the casting will expand and the dimensions will become larger, as we have seen already in the table before. Due to the chemistry, and that's the CE value, will expand during the solidification. If this expansion gives a big pressure that is larger than the mold strength, the mold casting cavity will increase, and consequently the final casting dimensions will be larger. So we must see what's the expansion we can get, and secondly, what's the strength of the mold. Both play a role. And here we see something very important. On the left side, you can see if the casting is, let's say, cooling down and solidifying, we see that during the first phase, the shrinkage is very, very, very much. But the moment that the graphite is segregating, that we are becoming to make nodules, then we see that there is an expansion again, because free graphite has a bigger volume when it's coming out of the metal. And then we go up again, and we get a pressure on the mold until the casting is completely solidified. The A is, let's say, high quality of the liquid metal. Then there is that difference between shrinking and expansion is few. But C is a low quality liquid metal, and then we have a big shrinkage first and a big expansion later and we can get problems. The pressure on the right side, we can see that the pressure due to the carbon segregation, thus making nodules or making, lamellar flakes, you can see depending on the modulus of the cast. When you have a modulus of 1, that means the casting is 20 millimeters thick. And we can see these curves are, let's say, my experience. During all the time we have looked for it, and they are not 100% correct, but they give a very, very good education what can happen. Why is ductile iron a bigger pressure than gray iron? Because the carbon equivalent is higher, and the graphite, there's more graphite in it, and the expansion will be much, much more. And that can go up, let's say, in big castings. If we see a modulus of 2, means 40 millimeters thickness, then we are already at 4 MPa pressure for ductile iron, and we are on about 2 MPa for gray iron. The thicker it is, the bigger the expansion will be, the more pressure will be on the mold. Now, how much strong is your mold? Next slide, we can see. These are figures I have here, and maybe it's not 100% correct, your Foundry, but the green sand hand compacted is about 1.5 MPa. A green sand machine compacted is about 2 MPa. Furane sand or chemical bounded sand is about 3.5 MPa. Water glass is about 4 MPa. And cold box shot core, the core is can be up to 5 MPa. Let's see now for green sand. We see that the strength is about 2 MPa, and for furane 3.5. If we go then back to the previous slide, and we see with 2 MPa in green sand, we can only make a casting up to, let's say, 25 millimeters for having the same pressure. If it's more than 25 millimeters, there will be an expansion in the mold. For gray iron, up to 25, it's nearly nothing. But for ductile iron, we have it. If we had chemical bounded sand, that was 3.5. If we take 3.5, then we see it's about up to 14 millimeters in ductile iron. Wall thickness that can, let's say, resist over the 40 millimeters, it will be. Now, when you have 100 millimeters or more, you can be sure that there will be a mold expansion, and shrinkage, if you measure it later compared to your pattern dimensions, will be very, very small and much smaller than we think it should be. How can you see that? You can see outside that there will be a bump at the casting. I did not put it on the top or the bottom, but at the side you can mostly see there is a kind of a bump there. If you have a hollow casting with a core and the core is not that strong, you can have somewhere in the middle where the casting, the metal is the longest liquid. At that place, the pressure will be the highest, and you will also get an extra dimension there compared to the bottom and the top. So 2 weak mold, 2 weak core compared to the pressure due to the carbon equivalent. Then the second one was the split line. If you have a split line who is opening a little bit, then we will have a higher dimension, and you can see that mostly the height I have indicated here, but also in the length it will be not, but in the height it will be bigger than we expect. And the heat treatment again will also increase the dimensions a little bit, but then in all dimensions, as well in the length as in the height. So the split line is a very important thing in your foundry production. Yeah. You see it on the left. I showed it a little bit in red. You have a flash there. If you have a flash, you have a bigger dimension, and many times due to the clamping, when the clamping at one side is okay, but at the other side not, you see that the flash at one side is much bigger than at the other side, and you get a totally different dimension compared to what you expect to do. So clamping is really very, very important. Also putting weight on a mold is important, because the weight must, let's say, cover the whole area of the mold where the casting is below. I don't know if you remember something like this. I see it so many times. Don't think the dimensions are okay with a flash like this. You can forget it. It will be a different dimension. And mostly the dimensions will not meet any more requirements as they are put in the ISO 8062. You see from time to time, you see flash from up to 5 to 10 millimeters sometimes. Okay, in a casting like this, mostly no one is saying something because it's a big casting, and if there is a little bit more in one side than to the other, the machining is only the flat side of the flange and not, say, the whole inside, but it's a different dimension than what you have targeted. The deformation, because this was the first thing that was mostly due to, say, the split line and a heat treatment. But you can also have a deformation who is due to the shrinkage restriction by too strong sand or mold or car. And due to that, incorrect dimensions will be there compared to the drawing. And it can also be that, let's say, the incorrect shape is due to an incorrect core, an incorrect connection core mold, or a bending of a core. Let's see some example. If we have left on the top, we see a kind of a T. There will be no restriction, and with this casting, you will get very close to the shrinkage who is in the rigid tables. It will be more or less okay. If we go to the top at the right side, and we have now something with two flanges, then between the flanges, depending on the strength of the mold, there will be less shrinkage, and the length of the casting will be longer than we expected, which means a less pattern shrinkage than we expected, and that can be even 0.5% and less if we have chemical bounded sand, because the sand is really very strong. Why did I tell you the strength of the sand is 3 and 3.5? Well, the casting solidifies really very quickly at the moment that the strength of the sand is still there, and the sand can become stronger than let's say the strength of the solidifying metal, and you can even have, in this case, hot crack in the corners. You can have hot cracks because the sand hold the flanges on the place, and inside that connection shrinks, and you can get hot cracks. Left bottom, you can see it a casting with two risers. If you have the riser, and in between the riser there is a strong sand, let's say mostly chemical bounded sand, then it will be that impossible for it to shrink over there. And what can you get then? It will bend. And how will it bend? It will be smaller at the bottom compared to the top, because at the bottom it can shrink without any problem, but not on the top, and the casting deforms. On the bottom at the right side, that's the most difficult part, because you can see there that between the two flanges in the bottom side, there is sand, and that sand will not move whatever, because it's really pushed inside, and the shrinkage will be nearly zero over there. While at the other side of the curve, there the sand can be pushed away, and there it will shrink more or less. And what we see then is that the flanges are not angular anymore on the connection, but even deformed. This is, let's say, now shown by very simple shapes, but in a complex shaped casting, it can be there in some areas. Always remember, something shrinkage can be hindered, can be decreased by the strength of the mold in between. Yeah, and then we have the deformation due to a mold and a car shift. In that ISO standard, there is also a table who gives you the maximum mold shift. There is an indication how much millimeters it should be maximum. And these are, of course, very serious ones, the examples there. But look at the standard, the 8062. There is a table giving the mold shift and the car shift. What you can have also is that you can have, due to the fact that your split line is, say, giving there an opening so that we have a flash, that the car who was exactly okay when we started, that at the end there will be an area below the car or on the left side above the car where there will be metal. And on the left side is fairly okay. You have to machine, but if there is no machining, then you will have to drill the hole yourself. But on the right side, what's the problem over there? That the gas who is made from the car there, that the gas can enter the liquid metal. So it's not only the fact that the dimensions will not be okay, but you will also have the danger that the gas can enter the metal over there. These are examples, and you see it. Don't say, I have never seen it. Every foundry has seen it. In the left side, you see really it's not in the center, it's side of it, mostly due to the fact that the car shoulder is not strong enough or long enough to avoid that the car is moving. At the right side, you see there that left is very thick, and right is much less. That's due a movement of the car. Then the bending, we know when we have a car who is fixed at both sides and is horizontal, he can bend, and you can have a casting like in the center you see there, that the wall thickness will be very few, even it will punch, there is an opening over there. Especially very dangerous is the right side. When you have a car, make sure that the car print there is really very, very strong and let's say dimensionally big enough to avoid that it will bend. And people have then mostly that they say, yes, but there must be a gap between the car and the mold. If there is a gap between the car and the mold, the car will move during the filling of the casting and it will not be horizontal anymore. You can forget it. So pay attention for that. And this is the surface sunk. You see it at side. These are bearing blocks, and you can see that there is a hole there. The top one, it's still closed. At the bottom one, it's open, and then everyone recognizes it as shrinkage there. But the top one, it's closed, and then they don't recognize it's at shrinkage. That's really very, very important, but it's a matter of shrinking liquid volume shrinkage during solidification. So, and it happens, the thicker the casting is, the more the risk it will happen. At the right side, you see the same, that it's always at the top side of the casting, top side as it is in the mold. That casting had no risers, and due to the fact that there's no risers, that foundry thought that there will be no volume shrinkage. Yeah, there was a volume shrinkage, and it had taken it, and you see on two places really very sunk in, and the dimensions are also not okay. Many times, if the wall thickness is still thick enough, some customers will accept it. The wall thickness is not thick enough anymore. When they machine it, then it will be scrapped, especially for wall thicknesses. This is a fairly big casting. It was 12 ton in ductile iron ferritic. The left and the right side had been the same, and you see that at the left side there are details are not correct there, and whatever happened, there is a car who was not put, so that we have a totally different dimension and not a dimension, a shape. So don't miss a car, and if you have cars, put it at the right place. Otherwise, you have a big difference. The machining allowance, machining stock, it must assure that after machining, you have the proper surface condition. The removing of the potential surface inclusion must be done. You have, especially at the top, it's very, very difficult to have ductile iron castings where there is no inclusion at all. Because in most casting, some dross will always be made. And if you machine it and the dross is not out, then you will see on the surface the indications of the dross very, very easily. So therefore, make sure that, especially on the top, you have a bigger machining stock, a machining allowance than in the bottom. And my experience is that for somewhat bigger ductile iron casting, the machining stock who is mentioned in the 8062 is for the top too small. Try to be able to get some millimeters more in agreement with the customer, because it will be necessary. Otherwise, if there is one time or another little bit more of these dross or other inclusions, you will end up with a casting who will be scrapped. For the machining allowance, then I put here some roughness conditions that you have in a sand casting, hot rolling, forging, a permanent mold casting, and so on. And you can see that for a sand casting, pay attention that you meet the surface condition that the customer is asking, and this roughness can be measured by equipment. Mostly, customer does not really require something, but from time to time he can become a little bit agitated and critical when it's too rough. These are normal roughnesses you can get from castings and others. These are, let's say, roughnesses we can have with different types of production, and we should always compare it with what the customer is asking. You see, for sand castings and hot rolling is the roughest ones. Die castings are much, much better. Investment castings are much, much better. And this is a graph. I have a relative, let's say, comparison between the different types of molding. And that's something we should say, because it can be that the customer thinks I can have something in green sand because green sand is cheaper than, let's say, a V process or shell molding, but he can have not roughness and the machining allowance he wants to have. You see that green sand is, let's say, the largest tolerance we will have. No bake sand, already better, but not very much better. The V process is again better, as well as the V process with loss foam. That's a better one, is much, much better. Relatively, it's like that. Then we see that ceramic molding, that can be the same like shell molding, but can also be less accurate depending on how you know. Permanent molds are very strict in tolerances. A plaster mold can be good, can be a little bit less good. Die castings and investment castings are in principle the best ones. Always look at that if you have in discussion with your customer and he has now castings, let's say in ceramic molding, and he comes to you because you have chemical bounded sand, the tolerances will be not as good, and let's say machining allowance must be different, otherwise you can get problems. These two ones are relative, but it gives a very good indication. You see that for ceramic molding compared to shell molding, you should have a bigger machining allowance because the difference can be much bigger. If we go back to the previous slides, then we see that a no-bake sand has, let's say, less difference compared to a green sand. A V process is better than a no-bake sand, and the shell molding is much better. But keep this in mind, that the tolerances, the relative tolerances of all the molding systems decide about the machining allowance. If it's less accurate, you need a bigger machining allowance. It's a little bit also indicated in the 8062 standard, but as I said, on the top, please take a bigger machining allowance, because otherwise, from time to time, it's not enough.
It was a really good presentation, Mr. Hendrieckx. Very, very practical and very crisp. Meanwhile, what we have done or we are trying to do is, during our past Nodutalks and other discussions with the foundries, they have come up with some problems, like why bismuth is considered harmful and yet it is used in inoculant today. So this was one of the questions we came across during our Nodutalk regarding the chemistry of the ductile iron. So we have tried to present it again, what Mr. Hendrieckx and Mr. Dr. Basutkar have answered that. We have tried to convert into a graphical presentation. So like harmful effect of bismuth is it's a subversive element. It degenerates the graphite, reduces the nodularity. But what are the beneficial use in a modern inoculants? It gives a high nodule count, improves graphite nucleation, works with a balanced amount of rare earth, and improve overall casting quality. So this is how we are trying to convert this question answer into pictorial representation for the benefit of the wider foundry fraternity.
This bismuth addition if your casting is less than 15 millimeters wall thickness, you will not have the negative effect. But if it's more than 15 millimeters, you definitely will have the negative effect.
Okay, it is 15 or 50?
It's between 15 millimeters thickness.
15 millimeters. Okay.
Yeah, then you definitely don't have it. But if it's the wall thickness is more than 50, you will definitely have it.
Okay, so we will try to include that point also in this graphic.
Yeah.
And next was, what is the recommended calcium and oxygen level in the ductile iron? So these also based on the answers. So we have tried to convert that into a graphical form. What is the permissible limit of subversive elements in ductile iron and its effects? So bismuth, antimony, tin, lead, arsenic, tellurium, zirconium, titanium, lead. I think it is no, yeah, phosphorus, aluminum, boron. So these are the what we have covered in the chemistry, ductile iron chemistry topic of the Nodutalk. Then one question was asked: what should be the suggested chemistry for 600 by 3 grade in a centrifugal castings with 12 thickness? So this was the answer given by Dr. Basutkar, and we have converted it into a graphic suggested chemistry based on the EN standard 1563. Like another question was asked, what are the advantages of using ferrosilicon magnesium with lanthanum? Because that is the recent trend amongst the foundries. To more and more foundries are going for the lanthanum containing ferrosilicon magnesium. So these also we have listed it out. So similarly, we are trying to convert the interaction between participants and our experts during the Nodutalk and during our exhibitions and other general discussions. And this we can circulate. We are going to circulate to all our customers as well as the foundrymen for their benefit. Contact us for their queries on my mobile number 982430290 or Hardik's mobile number, my brother Hardik's mobile number 98243 So I'll repeat again. We have uploaded the Nodutalks of past Nodutalks on the YouTube channel. And our next topic will be on use of high purity pig iron solution for many foundry problems.